Okay, we'll get started. So it's a pleasure to have Anil Ananthaswamy give this colloquium today on from LLMs to LRMs. I think many of you may have even read some of Anil's articles, Anil's books. Anil is an engineer by training from IIT Madras. But he has been involved now with science journalism and communication for, I think, 15 years or more. He has written 4 books, most recent being Why Machines Learn. But he has a book on quantum mechanics. He has a book on neuroscience. And his first book was actually on the astronomy and cosmology on some of the telescopes in the different parts of the world. So Anil spans, as you can see, even just from the books, a very wide spectrum of science, and I think quite a pioneering personality in this field. He has been recognized also with a Knight Fellowship from MIT, during the course of which I think he partially wrote his latest book. He is a distinguished alumnus of IIT Madras. And I really enjoyed interacting with him. We did a sort of a chat at some point a few months ago. And I thought he should be someone who we should have at ICTS. Actually, I should mention he has been running a science journalism course at NCBS for the last more than a decade. And that has actually been very successful in training people going into science journalism, a 2-week course at NCBS, which probably will be continuing as well. So anyway, with that, let me hand over to Anil to take us on the journey from language to reasoning.
Thank you, Rajesh, for that introduction, for that lovely introduction. And it's a great pleasure to be here. Though the room is a bit daunting, I think professors are used to this. I am not. So during lunch, a few of us were having pretty animated discussions about large language models. So I'm not sure about a lot of the things I'm going to say already, like, the LLMs, large language models, bring about such divided opinions that you start doubting yourself sometimes about, whatever you know about this field. But anyway, so I would like to take you through this journey, which it feels weird to call it a journey because it has happened in the last 3 years, literally, right? But how we've gone from things called large language models, which were themselves a big surprise a few years ago, to the onset of what are now being called large reasoning models, right? But before I get into this, I want to just present to you my interactions with a couple examples of my interactions with these LLMs as they came on the scene, just to give you a sense for the kind of questions these models bring about in us. So when ChatGPT came out, like a lot of people in cognitive science, I was particularly interested in this idea of whether language models can exhibit this thing called theory of mind. I don't know how many of you are familiar with this idea of what theory of mind is, but let me just explain it so that we're all on the same page. It's an idea from cognitive science, and it refers to this aspect of our own being, where if I'm looking at someone, I can hopefully be able to tell based on outward behavioral cues from the way your eyes are moving, your posture, other behavioral cues. I can theorize about what you might be thinking, and not just me, but all of us can do it. And it turns out that we're doing this all the time. We basically are making inferences about other people's beliefs, other people's states of mind based on outward cues, right? And we need this for conducting ourselves in society. Now, it turns out that this particular ability doesn't come about until about 3 or 4 years of age. So if you were to test children who are younger than 3 years of age, they won't demonstrate this ability. And there was a very nice test that was designed. It was called the Sally-Ann test to test this idea of when does theory of mind arise in developing children. So the test goes something like this. This was done using puppets. Can you all hear me? So it was designed using puppets. There are two puppets, Sally and Anne. And so the children are watching this puppet show. And in the show, Sally first hides a fruit in her basket. They're both standing over a desk, and there are two baskets, one in front of Sally and one in front of Anne. Sally hides the fruit in her basket. Anne's basket is empty. And then Sally goes out of the room. And when Sally is out of the room, Anne takes the fruit from Sally's basket and puts it in her basket and closes the lids. So these are opaque baskets, so you can't see into it. A child is watching this. A child is watching the fact that Sally first put a fruit in her basket and then left, and Anne switched the fruit from Sally's basket into her basket. And then Sally comes back into the room, the puppet, and the child is asked, where will Sally look for the fruit, right? Now, all of us will basically say, oh, we know that, well, let me forget about what we'll say. A child less than about 3 years of age will basically say, oh, the fruit is in Anne's basket, so that's where Sally will look for the fruit. So that child is unable to kind of infer that while the child knows that the fruit is in a certain basket, Sally doesn't know it. So in a sense, the child is unable to peer inside Sally's mind and realize that Sally has a false belief about what is happening in the situation. So, but if you ask a child about 4 years of age, they will be able to say, oh, I know that the fruit is in Anne's basket, but Sally doesn't know, so she will look for the fruit in the basket where she put it, right? So in this case, the child older than 4 years of age is able to theorize about the contents of Sally's mind. And when ChatGPT came out, a lot of cognitive scientists got very excited about trying to test these models with coming up with fairly convoluted notions of, you can't obviously pose the Sally-Ann test to ChatGPT because it has seen that it'll just do pattern matching and tell you the right answer. So that doesn't help. So, people were trying all sorts of things. And here was my attempt. And at that time, I was writing a lot about quantum mechanics. So Alice and Bob turned up instead of Sally and Anne. So this was the question I posed. Alice and Bob are in a room together. There's a table with 2 drawers. Alice takes off her reading glasses and keeps them in the left side drawer. If Alice wears the wrong glasses and reads, then she gets a severe headache the next day. Keep this in mind. And the question continues. It's in the same context. Now Alice leaves the room. When she's outside, Bob removes her glasses and puts them in the right side drawer. In the left side drawer, he puts a pair of glasses that look exactly like Alice's but have the wrong power. He closes both drawers, so there's no way to tell that he switched Alice's glasses. Alice then comes back, takes the glasses and starts reading. How will she feel the next day? Think carefully and answer. So this was the question. You can see that this is exactly like the Sally-Ann test with a few indirections added so that hopefully you're not giving an exact pattern to match here and asking the LLM to come up with an answer that, let's see what it is. So this is what ChatGPT said. This was, I would think, early 2023, if I'm remembering right. So this was the answer. Since Bob switched Alice's reading glasses with a pair that looks identical but has the wrong power, Alice will unknowingly, that underlining and italicization is mine. I'm just doing that to illustrate the words it has chosen, which are demonstrative of what a cognitive scientist would say is theory of mind, right? So Alice will unknowingly use the incorrect glasses when she starts reading. As mentioned, if Alice wears the wrong glasses and reads, she gets a severe headache the next day. Therefore, Alice will have a severe headache the next day as a result of using the wrong glasses. So this was the answer. And then I asked further, why will Alice unknowingly use the incorrect glass? And again, a fairly reasoned answer. Alice will unknowingly use the incorrect glasses because Bob switched her reading glasses with another pair that looks exactly like hers but has the wrong power. When Alice returns to the room, she is not aware of the switch and assumes that the glasses. So you can see that there are words now that are being used that are kind of indicative of what might be happening in Alice's mind, right? So a cognitive scientist looking at this answer, if it was coming from a human, would say that this is demonstrative of theory of mind. This was 2 years ago, and then just for this talk, I decided to try this out with DeepSeek. Same question posed to DeepSeek today, well, the last month or so. And this was the answer, right? Now, I mean, the answer is no different. It's just that the process is different. If you look at this, right, what it's doing, it's saying to itself, let's break this down step by step. Initial situation, Alice puts her career classes in the left royal while Alice is out. So it's kind of going through an entire process of reasoning, or what quote unquote seems like reasoning, because you have to be careful with these words, and comes to a so-called reasoned answer. The answer is Alice will have a severe headache the next day, right? But this is a much more elaborately thought out answer than what ChatGPT gave 2 years ago. So, and these are actually illustrative of the two different systems. That the previous one was a large language model. This is a large reasoning model. And this will become clear as we go along as to what is happening here as opposed to the model from 2 years ago, right? Now, normally when I give this talk, and this audience uses LLMs way more than most people in the audience that I give talks to, but so this is not relevant as much. But normally, I would ask the audience, like, if you just had access to that information that you just saw, and if you didn't know anything about how LLMs work or how they function, how they're built, etc., would you say that what you got was a reasoned answer, right? Now you have to put aside all your PhDs and tell me, like, if you just saw that, what would you say? How many would you say that that was a reasoned answer? Just saw that. That's what, that's the key. If you just saw that answer, you didn't know what was behind that. Most of you will say, yeah, that was reasoned, right? Yeah, yes, it's a theory of ChatGPT, exactly. And what has been amazing in some of these talks is, I remember giving some version of this talk before large reasoning models came along, when it was just ChatGPT, and this was back in Germany. In the beginning of this was completely to a popular audience, like the city of Heidelberg. And I asked this question, almost everyone in the room put up their hands in the beginning, and at the end of 50 minutes of talking about how LLMs are built and asked the same question, and more than half the hands had come down. Nobody thought that it was reasoning. So, and I would imagine, if I didn't ask you to ignore what you know about LLMs, you'll probably say that they're not reasoning. But saying that, I just want to give you some historical accounts of, the hints that these things are quote unquote reasoning were beginning to appear actually well before ChatGPT came on stage. So in March 2021, UC Berkeley researchers, they released a data set. It was called the math data set. It was about 12,500 fairly challenging competition mathematics problems, something like that. That's a problem from the data set. So Tom has a red marble, a green marble, a blue marble, and 3 identical yellow marbles. How many different groups of 2 marbles can Tom choose? The solution is there, and the answer is supposed to be given in with a single numerical number with brackets around it, right? That's the way it's supposed to be solved. So not terribly difficult, but not trivial either, right? So, and this was the data set that was created in March 2021. And when they tried it out, apparently there was a CS PhD student who did not especially like mathematics in UC Berkeley, who only scored 40% on that. A 3-time International Math Olympiad gold medalist got 90% on that data set. GPT-3 at in that time frame, 175 billion parameters. This is just before ChatGPT came along. ChatGPT was built on GPT 3.5, so this was the model just before that. 175 billion parameters. It managed only about 5% of the math data set, right? It was accurate on only about 5%. And in that paper, in fact, in the abstract of that paper, the authors said, we find that simply increasing budgets and model parameter counts will be impractical for achieving strong mathematical reasoning if scaling trends continue. While scaling transformers is automatically solving most other text-based tasks, scaling is not currently solving math. And we'll come back to as to why this is relevant in a bit. But they were basically saying that something like the kinds of problems that were in the math data set would not be amenable to what was being observed otherwise, these scaling laws that were already beginning to appear, which were suggesting that as you just make these models bigger and train them on more data and give them more compute during training, they demonstrably get better in terms of the tasks that they are being asked to solve. And they were saying that, well, that might be true of text-based tasks. It won't be true of the kinds of problems that are there in the math data set. So around the same time, there was a company called Hypermind that conducted a crowdsourced poll. And this was their question on the poll. On June 30, 2025, which is about now, what will be the state-of-the-art accuracy of a machine learning model on the math data set? And experts at the time said by June 30, 2025, the best AI will be about 73% accurate. And it turned out that within a year of that poll, Google's Minerva, which was basically a fine-tuned model on top of Google's PaLM language model. And at that time, PaLM, about 500 billion parameters, was the largest large language model there was. And Minerva was then PaLM basically fine-tuned on text that was specifically about math. And I think they took papers from the archive and curated those papers and just trained it further on more high-quality scientific and technical content. Right? And already within a year of that poll, Minerva had cracked 50%, way before people thought that was going to be possible. And that math data set had questions like this. This is actually one of the answers from Minerva, right? And this is just a little cut and paste from the paper. So the question was, a line parallel to y equal to 4x plus c. 4x plus 6 passes through the coordinate 5, 10. What is the y coordinate of the point where this line crosses the y-axis? And this is the model's response. So you can read that and what is amazing is that this is just token by token prediction, right? I mean, it's just predicting. And that's the thing to keep in mind in this whole way of thinking about what these LLMs are doing. Because, if you just think about, you're given that set of, words as the prompt, and all it's doing is predicting the next word to follow. And what follows is what seems like a reasoned answer to again, not a trivial question, right? It's, again, for mathematicians, very trivial, but I mean, if you had given this to a high school student, it'll take a little bit of effort. And so this was, 2022. Already Minerva was getting, and it of course made also from, it's important to point out, it scored 50%, right? So which means it got 50% wrong. That's also important. So this is just to set up the whole idea that even in 2022, people were beginning to talk about this idea that, okay, there's some reasoning going on here, but we're not quite sure how to even parse it. So just so that we're all on the same page, for the next couple of slides, next few slides are going to be very trivial for most of you, but just so that, if there is somebody in the audience who doesn't know something about how LLMs are trained, I just want to go through it briefly. So a large language model, that yellow box that you're seeing, it's actually a black box. It's a large neural network with, in today's language models, hundreds of billions of parameters, which are the strengths of the connections of the artificial neurons that make up the deep neural network. So what you would do is you would give the large language model some text. In this case, the dog ate my blank, and it's supposed to predict the next word to follow that. And if you were in the US, turns out that this is a very favorite sentence, apparently, for kids to use as an excuse when they don't want to submit their homework. So there's a lot of text on the internet with this particular phrasing, the dog ate my homework. So the LLM, even though ate and my, the two words preceding the blank, are suggesting like, lunch, dinner, etc., that's the moment there's a dog in that sentence, that the accurate prediction for that word would be homework, right? So the way you would train the LLM is you would take that large neural network, and I'll come in a bit to what's inside. You collect as much text data from the internet as possible, and this is of course text-based LLMs I'm talking about. You're now beginning to do this with other modes of data. You take some piece of text and you mask the last word and feed that to the LLM, right? So in this case, you take the sentence, the dog ate my homework, you mask the last word, which in this case is homework, and you feed it to the LLM and ask it to predict what the last word is going to be, right? And in the beginning, it's going to make an error. Right? It'll probably most likely say lunch or something pertaining to food, and obviously that's wrong in this case. And the training process is going to calculate some sort of error in some high-dimensional embedding space between the correct answer, which in this case is homework, and the thing that it predicted, use that error to then figure out how to modify the parameters of the neural network so that the next time you feed the same sentence, it's going to predict a word that is closer in that embedding space to homework than what it said before. And slowly, by tuning the parameters, you will make it come up with the correct answer. But the key here is that it's not just done for one sentence, but obviously for every piece of text that you encounter on the internet, which means that regardless of what you feed it, if you mask the last word and you feed a sentence, its parameters are tuned now to be able to correctly predict the next word, right? So once the LLM has been trained like this, in a manner of speaking, the parameters of the model embody the syntax of human written language and even some of the semantics. And this is a debatable point about how much semantic knowledge it has. People are going to, especially linguists, will argue endlessly about this, and it's worth arguing about because, the semantics of semantics itself is a debatable thing. So no wonder people are going to argue about what it means here. But again, if you didn't know what was on the other side of the black box that you were dealing with, you would be hard pressed to say that it doesn't have semantic understanding. The questions that we saw earlier about theory of mind. I mean, in order to answer that, if you didn't know that this was doing some sort of next token prediction, and that's all it was doing, if you just took that whole thing as a whole and saw the answer, you would say, yeah, that displays a certain level of semantic understanding of the question, right? But anyway, so no one is debating that the parameters embody the syntax of the written language on which it has been trained. There is debate about whether it actually is also embodying the semantics. The basic process is this: the words come into the input side of the LLM. These words are converted into vectors or embeddings. Then these embeddings basically flow through that box that I'm calling the LLM, but there are actually multiple layers of neural networks there. Each layer is what is called a transformer layer, and that each layer of that LLM is taking the input vectors and essentially using this thing called an attention mechanism to recontextualize the vectors. So the vectors keep getting massaged as they go through each layer, such that they start making more and more sense about the different words that are there in the sentence, right? So essentially, if in that particular phrase, the dog ate my blank, if you had to predict just based on the first word that appeared before the blank, if you were just looking at my, you would make a completely wrong prediction. You would basically say, it could be anything. Anything pertaining to me would be a valid prediction after the word my. If you just use the next two words, ate and my, to predict the word that follows ate and my, you would most likely make a prediction that has something to do with food. Again, it would be wrong in this case, right? So you need context here. And context here is 3 words away from the last word. So the dog is the one that really triggers the fact that the last word has to be homework, right? And as sentences get longer and longer, predicting the word that is to follow all the words that you've given really depends on looking all over the sentence to find the right context to be able to say what comes next. And so that's what each layer is doing. It's recontextualizing the vector embeddings such that when those 4 vectors keep moving through the layers of the large language model, when they come out on the other side, they have so much context that has gotten embedded in them that you can take the last of those 4 embeddings and use that to predict the next word. So that's the job of the box that you're seeing. It's essentially turning all those input vectors into contextualized vectors such that the last of those contextualized vectors now has enough information to make a prediction about the next word, right? And a little more detail about what that, let me see, does this have a, so the input comes in on that side. That would have been your 4 words, so 4 vectors. And those vectors, rather the 4 words are turned into 4 vectors with the input embedding layer. The positions of words also matter. So those 4 vectors are then given more information so that they capture something about what position they are in relative to each other. And then those 4 set of vectors now, which are positionally contextualized, will flow into a transformer layer. And inside the transformer layer, each vector that came in is then turned into a set of 3 vectors. These are called query, key, and value vectors. We won't go into the details about that, but basically what is happening is each of those input vectors that come in, you use the parameters of the model to generate 3 vectors each for each of the inputs. So a query vector, a key vector, and a value vector for each of the vectors that came in. And if you stack all those query, key, and value vectors, you will get 3 matrices, right? You'll get the Q matrix, the K matrix, and these are calculated matrices. And essentially, again, no need to, I won't have time to go into this, but basically what this thing is doing is using this formulation to contextualize a set of vectors that came in, and then it spits that out. And if there's just one layer, then those contextualized vectors will then go into another linear layer of a neural network, and then into something called a softmax layer, which basically generates probabilities. At this stage, what the model is doing is it's saying, I have a vocabulary of, let's say, 1,000 words. Here's my probability for each one of those words as being the most likely next word to follow the input that came in, right? So this is essentially a probability distribution over the vocabulary. So whatever the vocabulary of the LLM, we're talking about words. Actually, LLMs break up your input not on word boundaries, but there are other ways of breaking them up. It's not necessarily on word boundaries. But the point here is at the end, what you get is a probability distribution. So input, you got, let's say, 4 words, the dog ate my. And what comes out here is a probability distribution over the entire vocabulary, which says that the most likely next word is homework, right? And that's what this is learning to do. And the way it learns is, in the beginning, the output probabilities will be completely wrong. It will probably say dinner, the dog ate my dinner or something. In this case, it is homework. And so the probability for the word homework in that distribution should be the highest, not the probability for the word dinner. So you would essentially calculate a cross entropy loss between the output probabilities and the ground truth probability, which because your algorithm is the one that masks the last word. So you know that the last word is homework in this case. And then you use your backpropagation algorithm to do gradient descent and modify the parameters of the model. And if you keep doing this for each sentence over and over again, by just masking the last word and asking it to predict the word that was masked, it learns how to calculate the correct probability distribution given any input text, right? It'll produce the output probabilities. So this is during the training. And then you would have heard a lot about how LLMs are things called autoregressive models. And that term applies to inference. So once you have a trained or what's called a pre-trained language model, which, by the way, I've just shown you one transformer layer here. You can have hundreds, one after the other, and each layer is going to do a different kind of contextualization of the vectors. And you can have, so there are multiple ways in which this gets more powerful. One, you can have multiple layers, but within each layer, you can have, so what you're seeing inside this one box is what's called an attention head. It's paying one kind of attention to the 4 words that came in or whatever set of words that came in. You can have many of those attention heads working in parallel. So your, words are paying attention to, let's say, a noun, or rather a pronoun wants to know what is the noun that I'm a referent for. So we don't quite exactly know what those attention mechanisms actually are learning about what's in the input, but you can have many of them in parallel and many in serial. So, yeah. Yeah, we don't know what exactly the attention mechanisms are picking up on. So we are saying that, you can kind of come up with very high-level notions of, let's say you had a long sentence, and one of the things that you need in order to make a correct prediction about the word to follow is that every pronoun needs to know what noun it's referring to, right? So that's just a linguistic way of saying that every pronoun needs to pay attention to every other word in the sentence that came before it and be able to pick out the noun that it is connected to, right? Now, is that exactly what's happening in there? We don't know. I mean, it's not like you can decode those query key value vectors and say that's what is being picked out. If it was a small data set, a very curated data set, limited thing, maybe you could, but in these large, huge things, there's some very complicated things and probably hierarchical things happening, right? Mm-hmm. It cannot be traced in the sense of you can't look at the weights of the neural network and say, okay, this is what it learned. You see, I mean, it's not like there's one attention head for paying attention to pronouns and one attention head for paying attention to adjects. I mean, those are not clear because this is so distributed. So any information that it's learning will actually be distributed across the weight. So you can't completely decipher based on the values of the weights and parameters that have been learned as to what each weight is responsible for. Each weight might be responsible for multiple things. So it's hard to decipher it, which is why neural networks are fundamentally black boxes. No, that's a slightly different problem. So, if you trained it perfectly well, right, where it was making no mistake on the training data that it had, then the randomness is something where it comes at the very final stage. You see this softmax layer here, right? It's outputting a whole bunch of probability. It's a probability distribution that is being outputted. You have to sample from the distribution in order to produce your next token. And you can here do a completely greedy deterministic sampling. You're saying, I'm always going to take the most likely next word. Or you can have some stochasticity here itself in the sampling. So when you increase the temperature of your large language model, this is the place where you're changing. No. This is completely deterministic, exactly. Is that the question that you are getting? Yeah. So the algorithm it'll do the same thing every time. If you give it after it's been trained, if you give it the same set of input vectors, your weights haven't changed. What comes out at the other end will always be the same because it's doing the exact same computation, right? What it learns are those matrices that allow you to calculate the QKV matrices, right? Or rather, it learns the values for those matrices. But once it's learned, it's a deterministic process. The only stochasticity comes at the sampling part, at the fine. When you increase the temperature of your language model, right? Then maybe you don't always sample the most likely next word. You might sample the 5th likely next word or 10th likely next word, and that's what gives it a little bit of variability in its output, right? So the inference part is you sample from the distribution, you take the next word, you append it back to the input, and you keep doing this over and over again, right? So if you gave it 10, like if you take the theory of mind question that I had, now go back to thinking about how weird it is that it gave us this answer about Alice and Bob, right? I just gave it a bunch of text. It doesn't know anything about, I mean, it's just looking at the whole bunch of text and saying, what is the most likely next word to follow that piece of text? It generates that, takes that piece of text, appends it back to the input you gave, generates the next piece of text, right? Next word, not even piece of text, just next word. And it's going word by word by word. And at the end of it, when you look at what it has produced, it looks like an answer to your question. This is what surprised people so much, right? The fact that something as an algorithm goes, this is fairly straightforward. There's nothing very sophisticated about it in terms of what it's doing. But the behavior that comes out, because of the scale, because of how many parameters there are in the model, how much data is being used to train the model, how much compute is being used to train it, it starts showing surprising behavior. And I'll come to that in a bit. So
that word unknowingly that you had. I mean, that was a kind of superfluous word syntactically, right? I mean, you could probably not have the sentence could have made sense.
Alice will use the correct classes. Yeah.
Why did that token use that word unknowingly? I mean, sense that is there something that
no, so here's the thing, right? If I post this at that, like in 2023, if I had given this to a Google model or I don't know if Anthropic had something at that point, it might have come up with a slightly different phrasing, right? It is. So in that sense, this output unknowingly is a consequence of its training procedure. The statistics of the language that it has encountered, right? It's fundamentally just statistics going on here.
Similar
The-
phrases in
Yeah.
happened in
So this is probably just pattern matching happening here, right? It has seen this much, and remember, as part of its context, it also has your entire question. So this is what amazes me. You know, you've given it this question, and it starts by saying, what do I need to do? The first word it produces is since, and then Bob, and then switched, and then Alice. There's no way, if you read all this, there's any way to predict that it'll come to this point, but it does, including using words which are potentially superfluous, but read well, right? Give you a hint of what is going on. So yeah, no, I agree. And there's a lot of such things here. You could have taken away those words and it would still be a fair answer, right? And then DeepSeek does something even more where it's actually, so by the way, in DeepSeek's answer, I haven't italicized anything here. This is exactly how it spit it out. It has emphasized what it's doing as being important or relevant. So and all these words are what the LLM spit out, key detail, conclusion, but which to you can see the sort of step-by-step reasoning process appearing in the output. But again, just remember that it is producing word by word by word. So which is why, yeah. Yeah.
previous words are acting like a context,
Yes.
even in advance.
Yeah.
Suppose I say that whatever is your fifth word in the answer, print that word as the last word of the answer.
If you said that in your context. Yeah.
Print that repeat it in there. Will it be able to do it?
Actually, I don't know. I haven't tried that, but it might. I mean, it really depends on what it is in the context that is the most overriding. Remember that all it's doing is that every step, what it does is it calculates a conditional probability distribution over your vocabulary, right? Given the context, it calculates what is the distribution over its entire vocabulary and then samples from it. When you put in new words in that context, including, it doesn't actually know what those words mean. It just there's more words in that context. That basically changes the shape of the high dimensional probability distribution that it has to work with. And you're statistically driving it to some other location in that manifold, right? And it may or may not, I don't know the answer to that. Like this is a, a statistics process that's unfolding, right? So, Shruvat, you had something?
Yeah,
No.
but
Yeah.
I just want to add something.
Yeah, please.
The addition is the models you interact with are not pre-trained. It's instruction. After the pre-training process, there's also an additional layer of fine-tuning which is always put in. So that's why models obey instructions. So you'll very rarely interact with the pre-trained model unless you go download it off Hugging Face. So the instruction tuned model is trained to follow instructions, so it might obey your instruction because it's told to give higher weight to that.
Yeah.
After this whole process.
Yeah. So in fact, I think that might have been the next slide. Yeah. So yeah. So exactly what Surat said, that what I talked about so far is pre-training. Like you can still find open source, open weight models just pre-trained, and you can play with that and you'll see. In fact, you can take those models, play with it, and see that they react in a certain way. And then you can fine tune it yourself. So using supervised fine tuning to do instruction following, and they'll follow it differently. And in that supervised fine tuning data set that you have, you can train it to be pay more weight to your suggestions that come in the context, potentially, right? It depends on how good your data set is. But basically, pre-training refers to the initial training of an LLM. This is the raw stuff, right? And this involves what's called self-supervised learning. There is no human in the loop here, right? Which is one of the biggest reasons why this has been such a big deal, because you could not have done this at this scale if there was human input necessary at every stage, right? So the initial pre-training is completely self-supervised. All you need to do is take some sentence from the internet, mask the last word, teach it to predict the last word, and you just automate that process for all the text that you can scrape off the internet, right? And then you come to what Shubrat was saying, is that you have to then turn them into chat bots or make them skilled at some task. Then you need to create or curate a data set of question answer pairs in the way you want it to respond to you. So ChatGPT is a supervised, fine-tuned model that interacts with you like a chatbot, right? It kind of has that format. And all that formatting is there in the data set, but this is now supervised fine-tuning, which means that humans have to create this data, and then you do the same process again. Next word prediction on a data set, but that is specially curated by humans. So obviously this is a much more expensive proposition. The only thing is this doesn't have to involve a lot of data, so it is still relatively cheaper compared to the pre-training. But if you had to do this for the entire pre-training stage, this would be prohibitively expensive. Then even after supervised fine-tuning, you can have chatbots that are, for instance, terribly rude or completely willing to give you dangerous information, like how to create bioweapons or something. And you want your LLM not to be able to do that, or at least try and, you want it to put as many guardrails as possible. So then you do something called reinforcement learning using human feedback to align them to human values. So again, this involves a lot of curated data where humans have to figure out what is considered a good response, what is considered a bad response. And then you use that data to do reinforcement learning on your model so that they are now being steered towards what are considered good answers and away from what are considered bad answers. This does not mean that this will always work. It's just like a guardrail, and it's been amply shown that they can be broken. It's not terribly difficult to overcome these guardrails. But anyway, these are the terms that you will see more often than not. But still, right, to me, what was amazing in 2022 was, almost no one expected a model that simply predicted the next word or the next token to be capable of such sophisticated behavior, including some of the math things that we saw. Basic stuff, but still, right? And even before GPT 3.5, which was what ChatGPT was based on, there were empirical suggestions that were showing that as models got bigger, in terms of more training data, more parameters in the model, more compute being used for the training, they got predictably better at next token prediction, right? So the loss that they were making on predicting the next token was predictably lower if you kept increasing the model on these axes. And so this was before, the first set of these kinds of observations came before ChatGPT was released. So obviously internally OpenAI, etc., knew about it because they were the ones who had actually the first paper that came out on this scaling law, which I'll come to in a moment, came from OpenAI. So this has actually, the fact that this was self-supervised learning, no human in the loop, and then this kind of empirically observed scaling laws, these were what drove the industry to saying we're going to invest more and more and more in terms of making these things bigger and bigger, because they were also observing surprising behavior coming out when they got bigger, right? But then and this is going to be towards the end of the talk, that so far I've talked of the compute being used during the training phase. And when you do inference, right, when you use the model, you ask a question and it just spits out the answer, whatever compute that might take, however many tokens it needs to produce, that many passes through the language model and it spits out your answer. But there has been a sea change in the last 6 months to a year, where it's using more and more compute on the inference stage of the process. Like it's actually, quote unquote, thinking again. These words, you have to be really careful, thinking, reasoning, etc., because they are kind of anthropomorphizing these LLMs, and we tend to actually attribute these sort of characteristics to the models. Whether they're actually doing those things in the way we understand them in humans is a matter of huge debate. It's also funny that when I give the talk, I'm much more circumspect about the use of these words, but when I'm sitting across a lunch table arguing with others, I have a very different way of arguing about these things, but that's how it goes. So anyway, the benefits of scale, right? So here's what happened, right? GPT-3, which I talked about earlier, which scored only 5% on the math data set, was 175 billion parameters. Soon after that came Palm from Google. GPT-3 was OpenAI, Palm from Google, which had 540 billion parameters trained on internal scale data. Minerva, which was Palm, then further fine-tuned on scientific and technical text specifically. So it got better at solving math problems. And this was the one that got 50% on the math data set, right? And this enabled so-called, again, quote unquote, emergent properties. Emergence is a hugely problematic term to use, but it's been used very liberally in the context of LLMs. And I just want to talk about it in the context of something called chain of thought prompting, which I'll come to in a moment. But and there's a particular definition of emergence that is used in LLMs that we need to be aware of, and I'll again come to that. So here's what chain of thought prompting is. This is from a paper that is Jan 2022. It was work done using GPT-3, so pre-chat GPT. Here's the input. Model input is Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And this is all part of the prompt. So this is a sample question, a sample answer, and then you ask your question, right? So your sample question, your sample answer, and then you ask your question for which you need an answer, and the model outputs it and it gets it wrong, right? This was GPT-3. And then what the researchers discovered is that instead of just saying that the answer is 11, if you just give it a little bit of information about how you as a human solve this problem. You provided the model with your chain of thought, right? How did you think through the answer to that question? That's now part of the prompt. And then you ask the same question that you did before, and it gets it right, right? Now its answer is not just that the answer is 9, it actually has some sort of output that seems to suggest that it is reasoning. But remember, all that has happened is when you had this, right, the conditional probability distribution that it calculated, that high dimensional surface, had only this as the condition, and it was predicting wrong. Now you have some extra information, and you've essentially changed the shape of the conditional probability distribution that you're making it calculate, right? Yeah. Where? Oh, who knows how it got it, right? It just got it wrong. It's hard enough trying to answer why it gets it right. It's worse when you ask it why it got it wrong. Yeah. 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 Yes. Yes, except, absolutely, I'm not disputing that at all. That's absolutely the case, except that when this happened, right, this did not work with GPT-2. Remember that GPT-2 and GPT-3 are trained exactly the same way. Same algorithm, nothing changes except the size of the model. So there was no in principle reason to expect that just by making something bigger and giving it more training data, you're going to get behavior that is demonstrably, predictably better, right? So that was a surprise. Your intuition about why it should do it is absolutely right. Of course, right? In fact, you can argue with the same intuition that if you have a more powerful model, in the sense that you have more parameters, you now have given it the ability to calculate a more complicated probability distribution, right? You're giving it. Yeah. So if you teach it that way, when you give it more data, then it will give you better predictions. I'm not disputing that. You're right. But the other thing is, if you just take the same question now, right? Like if you take this entire prompt, you don't even have to give the initial answer. You just have to give this question now to today's LLMs. They don't even need the extra context. They'll answer this correctly, right? So something is changing. And I think the question to ask for researchers is, what is it? Why is scale doing it, right? But the intuition is correct, that of course they're going to do it, right? That's exactly the point that is being made here, that this extra information is essentially teaching it that, it could still have just, the question is still how many apples do they have, right? It could have still said the answer is 9. It didn't. It went ahead and did this whole thing, which is telling you that the prompt matters a lot, right? But the same prompt in a smaller model did not work. It predictably failed, right? The fact that you just made it bigger was important. So this is what then led to this race for bigger and bigger language models, right? You started seeing, so these were the first set of neural scaling laws that came out in 2020. Researchers at OpenAI had quantified essentially empirical observations that they were making about the cross entropy loss, which is the difference between the predicted probability distribution and the expected probability distribution, given the model size, the data set size, and compute. And they basically found these power laws, right? The loss scales as a power law with the number of parameters, with the number of training tokens, and with the amount of compute used during training. And they came up with, if you look at the paper, there are a whole number of different empirical formulations of these scaling laws. This is one where you say that the loss, which is depending on the number of parameters and the number of tokens, is given by this particular equation. Again, it turns out that these things are, well, first of all, they're empirically determined. So, and there's a lot of variation depending on what experiments they're choosing to run, right? So they've come up with something, but this was the one that was, this is the one that allowed OpenAI to actually kind of make a bet on making models bigger, right? Internally, they kind of knew that if they just kept making it bigger, the loss, the cross entropy loss that it makes on next token prediction is going to fall as a power, it's going to fall predictably. And they had also observed that as the cross entropy loss fell, there were emergent behaviors. So those two things were linked in their minds as to why they should keep making things bigger and bigger, right? But this neural scaling loss actually turned out to be not quite right, because it had recommended that for a fixed compute budget, you build a very large model and train it for relatively few tokens, or so they emphasized making the model bigger relative to the data. And OpenAI follows this recommendation from their own paper, of course. The scaling law paper also came out from OpenAI. They follow this recommendation, and GPT-3 was trained on 175 billion parameters, was trained on 300 billion tokens. This would turn out to be too small a data set. And then Google DeepMind, a couple of years later, came out. They pointed out some flaws in the OpenAI methodology and came up with a different scaling law. The form is the same, but they basically said their key finding was that model size and data set size should be scaled equally for some given compute, right? And this turned out to be, these were called the chinchilla laws because of the model that they were using. It turned out that a small model, in this case, something called chinchilla 70 billion parameters, significantly outperformed a much larger model trained on less data, which was something called Gopher, 4 times bigger for the same computational cost. So essentially, it turned out that it's better to train a small model on more data than a bigger model on less data, right? Even though both might give you the same performance. So obviously, if you're just looking at the training time performance, this doesn't really matter. You can get, if you get the same performance from a small model, more data, or a big model, less data, as long as the compute budget is fixed, you can choose either. Any guesses as to why the smaller model is better once the pre-training is done? Yeah. Sure. What's the size of the model? Size of the model is the number of parameters in your neural network that you need to learn, right? So these are just the strengths of the connections between the artificial neurons. The parameters of the model, just think of it as the knobs that you have to tweak, right? In order to, when you're training, during the training run, that yellow box that I showed you inside will be artificial neurons, networks of artificial neurons. So the number of connections between them. So that's the size of the model. And the size of the data is how many tokens or how many words that you have in your. So obviously, even though during training, it doesn't matter whether you choose a small model, big data versus big model, small data. During inference, it's much, much better to have a small model. If both of them are giving you the same performance, if your model is smaller, then when you're doing inference, the compute cost of doing inference is way lower, right? So you would prefer that. So again, these were all empirically determined laws, and they were very convincing to the community, saying that we just have to keep making things bigger and bigger and bigger. Of course, following some guidelines from these papers, right? So this is a definition of emergence that is used in the context of LLMs. An ability is emergent if it is not present in smaller models, but is present in larger models, right? And remember that they're trained identically. There is no change in the fundamentals of how these models are trained. All that has been done is, of course, there are engineering tweaks and all that we don't hear about, and pretty sophisticated things that are happening as they get bigger. But the basic math of what is happening doesn't change from a 70 billion parameter to a 500 billion parameter model. And so foundation models around summer of 2024, which is summer of last year, these were the ones that were making waves. There was GPT-4o, Anthropic had Claude 3.5 Sonnet, Google had released Gemini 1.5, and there were a few others from Meta and others, and this was a big deal. At that time, GPT-4o was considered quite a big leap forward. So was Claude 3.5 Sonnet. And there was very little hint of what was coming. And then suddenly, in September of 2024, the first so-called reasoning model started appearing. And here, the scaling, so the scaling that I've been talking about, like scaling simply means throwing more compute at the problem, and throwing more compute means you're using it because the model is bigger or because you're processing more data. And so far, the scaling has been referring to the compute you throw at the training part of the model, right? You're training the model using more compute. And there was a shift sometime in September last year. I mean, the models were released, so obviously the shift internally had been going on for maybe a year and a half before that. But September last year, OpenAI released something called O1. And so the OpenAI's O1 series of models came out. And then within months, other things started happening, and most of you will remember Jan 25 of this, or Jan of this year, when DeepSeek released its open weight reasoning models. And they were a big deal. And then, of course, Google's Gemini 2.5 Pro, and then Anthropic has its own set of reasoning models. So here, the key thing is, instead of a user providing a chain of thought as part of the prompt, which is what I showed you that example, right? A large reasoning model is trained using reinforcement learning, and I'll mention it briefly as we go along, to generate internally. So you just give it a prompt, and what it does is it internally generates explicitly or implicitly a whole range of chains of thought. And a chain of thought is simply a sequence of tokens that leads you to an answer. And that answer might be correct or wrong, but a chain of thought is simply a sequence of tokens. As far as the LLM is concerned, it's just a sequence of tokens. But when those sequence of tokens are turned into words and we read it, it looks like something that is being reasoned, right? So internally, it's essentially generating or searching through a space of possible chains of thought and selecting the correct one or an optimal one. Correct one if there is some way of verifying for correctness, or an optimal one if it is if it's based on human preference data, which can be slightly nebulous, right? And it essentially picks what it considers an optimal sequence of tokens and then produces the final answer. But what this has done is that this is now using compute during inference, right? The model is already trained, model is done, right? This part of the process now is using compute during inference. When you as a user are using the model, it adaptively uses more or less compute in order to answer your question. So if your question is really complex, it adaptively increases the amount of compute it's going to use in order to maybe search through many chains of thought or generate a very long sequence of tokens in order to get to the answer, right? If it's a simple answer, it'll do it quickly. But weirdly enough, these large reasoning models, even if you ask it a simple question like what is 4 plus 2, it will say thinking, and it'll spend a whole bunch of time trying to figure out what 4 plus 2 is. So it can work in weird ways. But basically, when your input prompt has something very complex that you're asking, it will adaptively use more compute during inference. So essentially shifting the compute burden to a whole different place. So this is the graph that OpenAI put out when O1 came out. So this is on something called the American Invitational Mathematics Examination, AME. And so on the y-axis is the accuracy of the model with one pass. It's just making one pass through at the inference phase. And here is the amount of time that was used during training. And you can see that the accuracy is going up as you're using more and more compute during training, right? And then they showed that because it was a reasoning model, now during inference time, if you give it more compute to spend more time on the answer, it also starts increasing the accuracy, the pass at the first one pass accuracy on your mathematics questions. So this is the scaling law that is the original one. And we have entered a new regime where there's a different scaling law that no one has actually worked out the empirical form of yet. Because there are many ways to do this, and I don't think people, and also these models are now so big, right? So the original scaling laws were done empirically on fairly tractable models. You're talking of 250 billion parameter models. We are now at a regime where we are probably at trillion parameters, and the data set sizes are so huge that to do empirical tests to come up with laws is not going to be trivial. But nonetheless, they're observing this kind of behavior. So if you just look at the neural scaling laws, this is from a blog post from NVIDIA. So if you have compute on the x-axis and quote unquote intelligence on the y-axis, thankfully they put it in quotes. So you can see that there is one scaling law regime that works for pre-training. And then there's a new scaling law that takes over if you do things during post-training. Once you have a pre-trained LLM, right? And then you want to fine-tune it, you want to use reinforcement learning. That's also compute that you're using to make its performance better. And performance is simply how good is it at next token prediction, right? So things that you can do post-training, I'll just show you a list of what those things might be. But that's another new regime. But what this final scaling regime is this one, test time scaling, where you're taking time thinking, quote unquote, to solve your problem, right? So we've gone from one fairly well understood scaling law, which is the pre-training scaling, to post-training scaling, and then to test time scaling. So this is where we are right now. Yeah.
This internally generated chain of thought applies only in the last.
Only in the last part, the test time scaling. Yeah.
But in the intermediate one, that's just some.
Which intermediate one?
The one.
The post-training is just, these are the kinds of things you can do in terms of using more computation to make your model better. So you can, fine-tuning, like if turning an LLM into a pre-trained LLM into a chatbot makes it better at next token prediction in the context of a chatbot. So so these are all identified. There's a whole bunch of things you can do to make your model better. So that's post-training, but this is not yet. So this might still do the old-fashioned LLM. This may not be a LRM, right? So this applies to both LLMs and LRMs. And then LRMs are the ones that then take over from here and start doing internal searches through chains of thought during inference. No, I don't think this is actually I think this is just an artist's impression of what they think is happening. So the only place where we have any idea quantitatively is the pre-training era. Everything else is, hand waving. And observed stuff, but this is just, don't pay attention to the slope. For all you know, it could be like that, or it could be like that. So it has been really frustrating actually for people on the outside to know what these reasoning models are doing. We know in a very vague sense from OpenAI, from Google and others, that what these models are doing is doing some sort of implicit or explicit search through a space of possible chains of thought in order to answer your question, right? The specifics are not available. Thankfully, about a month ago, so when DeepSeek came out in January 2025, they put out a paper that was on the archive. And then last month, that paper was peer-reviewed and appeared in Nature. So, and this has at least one clear indication of how this process might work. So I just go through it. It's slightly different from what might be happening in OpenAI's reasoning models, or actually we don't know we don't know whether it's slightly different or very different, but at least here there's some concrete indication of what these people did, and it tells us. So here's what's happening, right? So these colored boxes you see are your language model. So a frozen model is a pre-trained language model. And both the yellow and the trained model and the frozen model are the same LLM. One you freeze in the sense that you never change its parameter values after pre-training, right? It serves as your reference. And but then you want to now make that model better, right? In order for it to be able to generate, sort of use more compute during inference time in order to adaptively answer questions so that it takes more tokens to answer difficult questions and less tokens to answer sort of easier questions. And sorry, you said, yeah, eventually the better is simply, okay, maybe I'll talk through this figure here a little bit. So the policy model is you start with an LLM that has been pre-trained, right? You take 2 copies of it. One you freeze. You say that, okay, this is my reference model, and I have to keep that frozen. And then you take the same model, and that's called the policy model. And that is the one whose parameters have to keep changing because you're now training it to adaptively do something at inference time. So that's the policy model, right? So you give it a prompt. The policy model, which is your LLM, pre-trained LLM, takes in the prompt and generates a whole bunch of possible solutions. Then you have a reward model, and this reward model is slightly nebulous. In this case, depending on whether you are talking of DeepSeek R1 0 or DeepSeek R1 1, I forget what, R1? No, R1, I'll come to it. So there were 2 models. One in which the reward model was simply something that was only for verifiable things like math problems, logical reasoning problems. It could give you a quantitative reward at the end of, So essentially what the reward model does is it takes all the answers, possible answers. These are all sequences of tokens, mind you. Each one is a chain of thought, right? So the reward model takes each of them and gives it a reward. And then there's some group computation that is done, and those, they are all ranked relative to each other. And then this information is then used to update the policy model so that it generates, the best possible, sequence the next time. They're all ranked relative to each other. There's no external reference here. The other thing you have to do is you have to keep your reference model here, and at every token that is being generated by the policy model, the reference model is also generating the same token, and you're making sure that the 2 probability distributions that are one that is being generated by the reference model and one that is being generated by the policy model don't drift away too far from each other. Because if you don't have this reference model, reinforcement learning is such that the policy model can literally hack the rewards. It will end up doing something to gain more and more reward, and it will end up going very far away from your reference model, and you'll end up completely catastrophically forgetting everything that you've learned. So this is a way to make sure that your model doesn't veer away too far away from your reference model, while also maximizing the reward. So it's doing 2 things at the same time. The reward maximization is happening after the entire sequence has been generated, whereas the KL divergence constraint, this thing of keeping the probability distributions in check, is happening at the level of each token prediction. In this case, in R1 0, it was only for verifiable questions, right? So I think it was, let me see if I have it somewhere here. Okay, this is what I just told you, right? Yeah. I'll come to that in a bit. So this is how they did the training, right? So their training prompt template was this: a conversation between user and assistant. This is the actual template, this is why this paper is so amazing, that you actually see some of these details of how this was done. A conversation between user and assistant. The user asks a question, the assistant solves it. The assistant first thinks about the reasoning process in mind and then provides the user with the answer. The reasoning process and answer are enclosed within think dot dot think, right? These tags and answer in these tags respectively. That is think reasoning process here, think answer here, whatever. This is the prompt. This is part of the training. So in the case of R10, the rule-based rewards to deliver precise feedback for data in mathematical coding and logic. So all these problems that had a quantifiable way of saying, okay, you got it right or you got it wrong, right? And rewards were given for both for accuracy and format. As long as the model produced a chain of thought which was formatted like this, again, this you could verify using templates. So you could actually come up with a reward that was completely automated. There's no human involved in the picture here, right? DeepSeek R1, which was, there was something interesting that happened with R10, which caused them to also do R1, which had rule-based rewards for both reasoning-oriented data and so like R10, but also had model-based reward for general data, where they had to train a separate reward model using human preferences. So this again brought the human back into the loop, right? So they had a reward model that was a little more complicated, where it would look at the response and say, okay, this is accurate because I can verify it mathematically, or because it's a coding problem, or because it's a logical reasoning problem. Those were automated verifiers. But it also had a reward model which was able to judge whether the generated output was what humans might have said was good or bad, right? So, but that meant that the reward model had to be first trained outside of this whole process to incorporate human data, human preferences. But this is just a template. This is just part of the prompt. This is the, in every question that is being asked of the DeepSeek during training, this was the prompt. It was being told to generate answers in this format. This
assistant is always the model. Assistant is the model.
Oh, you're asking who is the assistant? Yeah. Oh, I see. Yeah. This is the model. The user is the human. In this one? So this prompt refers to the, the prompt that a human would provide, right? When you are using an LLM, right? This prompt template is basically telling the LLM to say that you imagine you are having a conversation between a user and an assistant, where you are the assistant, and the user is the person who is giving you the prompt. In the case of this training, for R10, there was no human involved in the process. This is why R10 was actually quite amazing. And I'll show you some of the outcomes of this. So so far there is no human involved in this loop, right? The pre-training of the model, when you froze the model and then started doing this reinforcement learning, the only other model here that is necessary is the reward model, but this is a completely automated verifier. It's only working on things that are problems for coding, for mathematical problems and logical reasoning, all of which have sort of easily verifiable answers. So nothing in this has a human in the loop. And this was what was amazing about R10, because then what happened is what they saw was as you increase the number of steps, and a step here refers to one update of the policy model or your LLM's parameters. Like if you update all the parameters of the model at one shot, right? That is called one step, that whole loop, right? So as the number of updates kept increasing, you saw the average length per response kept increasing. The policy model. No, the pre-training is done. The pre-training is done. You're taking the pre-trained model and doing reinforcement learning on it. No. The user is not in the picture here. Yeah. Yeah. So
happening. This is not inference.
No, so that's what I'm coming to. So that's the interesting part, right? So you're right in the way you're thinking about it, but what is happening to the model right, is what is the crucial part. So as you are, so listen, remember that it's being asked to produce an output in that template. So that's being checked. It's also being rewarded for answers it gets correct, right? So, and as the number of update steps are increasing, they notice that the average length per response is increasing. So far, we are not talking of accuracy, nothing, right? All we are saying is, as you're doing more and more updates on the model, your average response length is going. The tokens, yeah. The per response, like the O1, O2, O3, that series of responses, that's increasing. Yeah? There's no reason to a priori expect that to be the case, right? So then they see that as you're increasing the number of steps, they are looking at the frequency of certain words that appear in the output stream, right? And these are verified by human experts who look at that thing, and they find that words like wait, mistake, however, but, retry, error, verify, wrong. I mean, words that are indicative of the model telling itself, hang on, this doesn't seem right. Let me backtrack this, whatever, right? I'm just, we are anthropomorphizing here, but something to be really careful about. While these words might appear in the stream of tokens that are being produced by a model, it doesn't necessarily mean it's doing these things as in terms of what these words mean to us in this case, English language, right? And this is also a huge point of debate among experts about, does this really mean that it's thinking, or this is just it's outputting something and we infer it as thinking, and we don't know the answer to that. But what is interesting here is that the frequency of these reflective words keeps growing up as the number of updates are growing, and the frequency of the word wait, like you can see the spike, right? So something about its generation, it's almost like some student trying to answer a question and is saying, oh, hang on, wait, this is wrong. So there is reflection going on in a manner of speaking. I'll be very careful about.
One can always verify whether the wait is accompanied by a change of course.
Yeah.
That is not anthropomorphizing.
True.
So
I'll give you a very interesting example of completely anecdotal. I took so a few months ago, I was at the AI lab in Princeton, where I got to play around with some of these models, and I took a distilled version of DeepSeek, which generates a reasoning trace, so a smaller model that you can run on their GPU cluster. But because it's open source and open weights, you have access to the reasoning stream that's coming out, like token by token, right? So I asked it, what is the capital of France? And even to answer that simple question, it has to generate some, 4 paragraphs of tokens. But what was interesting was, as it was generating the tokens, I inserted a phrase saying, but what about giraffes? In the middle of that token stream. It doesn't know that it hasn't generated it, right? It just sees that whole thing is fed back, and suddenly it has generated one paragraph, and now there's one line there that has suddenly appeared saying, what about giraffes? And it's fascinating to watch its response after that. If you do it at the very beginning of its reasoning, it kind of gets, where did this giraffe come from? Must be important. And it starts muttering about giraffes but it hasn't completely given up on Paris and France either. So, but towards the end, it kind of tells you that the capital of France is Paris, and that zoos might be. So it hasn't also forgotten about giraffes, because it was there in the context very early on, and it says some stupid things about giraffes in Paris, right? But if you wait till almost till the very end, right, where there's only one paragraph left of its inference, and then you say, what about giraffes? It looks at that and says, where does this giraffe come from? It's completely irrelevant, completely ignores you. It basically says, this is not important. So, these words are important. You can see it changing course, and yeah. So I would imagine, depending on where weight comes, and all these words do mean something. But honestly, there's a serious debate raging about what this tells us about what's happening internally. These are all behavioral observations, right?
And of course, it's always very difficult to make sense of data plots like this.
Yeah.
No, I mean, is this over many iterations? I mean,
this is during reinforcement learning. This is during the reinforcement learning part. These number of steps are the number of updates that are being made to the model, policy model.
Yeah,
right?
I meant, but
I see.
One run.
Yeah. So let's say you have a reference model that has been trained with 4,000 updates. then they would have done empirical tests on that model and got this data. And they have combined the two plots, combined the two,
because
right?
it's completely erratic, right? I mean, there is, of course, a trend.
Yeah, I mean,
but,
there is a trend. I mean,
there's a trend,
I think this one is probably more, to me, more important.
so
Like this.
can't they do what physicists do?
So here, okay, so there's one more. This is more important. This one is more.
Very expensive.
Oh, hugely expensive, right? Yeah, yeah. This is a hugely expensive proposition. Yeah. So let me just finish this. This is the more important one. So as the number of updates increases, right, the model predictably, not predictably, but gets better at that AMI data set accuracy, right? This one, so this is the proof of the pudding, basically. So we know that as the model, as the number of updates of the policy model increased, it also got better at generating, its answers got longer and longer, but longer and longer answers also mean more and more accuracy. So it's kind of saying that that is its implicit search over a chains of thought, right? Sorry, yeah.
Some things here. This is an explanation of how DeepSeek uses a reward model and reinforcement learning to produce quote unquote better output, more accurate output with respect to verifiable data and alternatively as well. It is not explaining why chain of thought prompting in the other models allegedly led to
no. I agree.
Right.
I agree. So those are separate questions. Yeah, totally. This is not an explanation for why chain of thought works,
or even why inference time compute on other models.
What other models?
Let's say Google Gemini.
Oh, okay. We don't know. That's why.
So here, it's not even obvious that DeepSeek produces its chain of thought.
No. This was, remember, I used the word.
This-
I said it either implicitly or explicitly searches through chains of thought. If you think about what it's doing, like if it produces a set of tokens and then it says wait, and then changes its stack. That's kind of it has done a search through one chain of thought and said, oh, that's wrong. Let me take a new.
But if I do chain of thought prompting on a pre-trained DeepSeek model, this is not it.
No. If
I just take
you can still do chain of thought prompting,
right, and it's not obvious that the way in which it's generating the responses to chain of thought prompting is this policy, because the reward wasn't baked in.
No. So I agree. So this reinforcement learning is for it to learn change its internal.
No. I'm irrespective of that. I'm saying there's a distinction between the chain of thought prompting that was done in 2022 for all models.
What we argued here is that the chain of thought is emergent.
That I agree, but that it sort of uses the idea that the policy model and the reinforcement reward definition of that policy is a good model in the scientific sense for chain of thought prompting.
No, because so here's the thing, right? The original, when you think of the original.
So chain of thought presumably can be achieved multiple ways. This is a way to achieve.
Yeah,
and so
totally. I mean, I'm going to show you this. Okay, maybe we can go to this. Given that we don't know what Gemini and OpenAI are doing, there is one paper which tries to kind of come up with a generic overview of how you might do this implicit or explicit search. So what DeepSeek is doing. So okay, to answer your earlier question about the earlier chain of thought when you used it on large language models, not large reasoning models. Remember, when you put the chain of thought, that becomes the context every time that it goes through that auto-regressive loop. That is there in the chain, in the prompt, right? This is doing something similar when instead of you giving it, it's generating a chain of thought.
I understand that.
That's all.
I totally understand. What I am saying is this is a version to achieve chain of thought prompting through reinforcement learning.
Yeah.
And it's not at all obvious that that's what was happening in the LLMs when they were doing chain of thought.
Oh, I see.
There was no reinforcement learning.
Yeah. No, that's true. That's true.
Those are still unknown as to why they
showed
performance improvement so on and so forth.
I think that somehow goes to what you were saying, that just the fact that the model got bigger, right?
But-
Its capacity to model a much more complicated probability distribution got better. That's all.
I just want to sort of end with the fact that there are multiple examples where even like chain of thought prompting isn't actually used by the models to internally make arguments, right? There's these papers that discuss that.
Yeah.
Chain of thought itself can sometimes be hacked by the system to present what it thinks you think is reasonable, not actually what it's
which is why I really want to be careful about how we use these words, right?
And
the debate is very much alive as to what we infer from looking at this. Even calling these things reasoning traces is debatable, right? Is this actually demonstrative of any reasoning process? It's not.
Right.
It is.
And in a sense, there are no wrong answers because ultimately there's a probability distribution. And so to say that it got a wrong answer is kind of problematic. It sampled from a probability distribution and gave an answer. 27 is as good as the correct answer in the sense of a probability distribution. Now, we have a verifiable different notion of answer, which we want, which isn't a probabilistic definition. But from the model's perspective,
that's all it can do. That's all it can do.
Hallucinations, it's all.
Yeah, I mean, I find the word hallucination problematic because the process of whether it generates a right or wrong answer is always the same. So, I mean, it's technically always hallucinating or not, right? So let me just, so to me, this was the key plot, right? The fact that as you increase the number of updates you did using your policy to the policy model, it got demonstrably better at inaccuracy. And this is also correlated with the fact that answers are getting longer, right? And as the answers are getting longer, we also know that there are a lot of these so-called reflective words in the reasoning trace, which is causing the reasoning trace to switch from one direction to another, right? So this is in a way you can think of it as DeepSeek trying to search its way through possible chains of thought. It's finding one path, right, through that. So the LLM dynamically selects fewer. This was important, right? It selects fewer tokens for simpler questions and more tokens for complex questions. So the inference time is scaled up on demand adaptively, right? Once the thing has been trained using reinforcement learning, now it's capable of taking more time when the question is hard and less time when the question is easier, right? This was a big deal. What was, again, more important with R10 was that there was no human in the loop here, right? All this behavior emerged kind of through a completely automated algorithm.
So multiple prompts were tried.
Yeah. I don't know if the paper has the exact details about that data. So all these companies, even though they talk of open source, open weights, etc., open weights certainly, you know exactly what it is. Open source is a more nebulous thing. Not all the source is released. Data is almost never open, so we don't know what the training data is. You just have some hints of what it might be. These are actual words from their paper. Although we do not explicitly teach the model how to reason, it successfully learns improved reasoning strategies through reinforcement learning. This was important, right? No human in the loop. R10 demonstrates excellent reasoning capability. It faces challenges such as poor readability and language mixing. This was very interesting because if you looked at the reasoning trace, it made no distinction between Chinese and English language tokens and coding tokens, and it was just doing, which obviously tells you that this is not reasoning in the way we would reason using language, but it's doing something in its embedding space, which works for it. And so they had to then train it. The DeepSeek R1 was now further, the rewards model had human preference data, which included saying, generate your reasoning traces only in English, right? So, but the fact that this was, R10 was as powerful as it was without humans in the loop was a big deal. This is just the possible search strategies that you can use, right? You can do a best of n, you can generate all the chains of thought, you can select one at the best, assuming you have some sort of verifier or reward model to select. You can do a beam search, you can do a look-ahead search, just different kinds of searches. So it's possible that OpenAI O1, O3 models and Gemini's 2.5, etc., are using something along these lines. We don't quite know what they're doing. We don't have the details. I think we've gone through all this. So yeah, this is what I just told you. Saying all this, despite all these advances, the problems are still there. These things can still hallucinate. Even the best of reasoning models, they are getting better. But given the fact that there is no mathematical guarantee for correctness with a large reasoning model or a large language model, it continues to be a concern for applications where 100% accuracy is imperative, right? You can't tolerate any mistakes. The amount of data is immense that you need to train these LLMs. And it's possible that we have run out of good publicly available data to train these models. There's probably orders of magnitude more good, in fact, much better quality data in private hands, behind corporation walls, behind institutional walls, etc. How that gets used, I don't know. Most people have no idea how that's going to get unlocked. These models are not sample efficient, which means that they require enormous amounts of data to learn something, which is completely counter to how, let's say, humans learn, right? We require very few instances of data to learn something, and also to generalize from one problem to another, etc. So these models are not there at all. So consequently, they are huge energy hogs. This, though, of late, there has been much debate about just exactly how to evaluate their energy consumption. I mean, certainly they are energy hogs. They're definitely not as efficient as biological brains. Nowhere close. So there's something we are missing. Let me just go back to this thing, and I'll end. This is this was a slide from earlier where Minerva cracks 50% on the math data set. Remember that experts had predicted that by June of this year, the best AI will be about 73% accurate. And then this was a debate we were having at lunch about what happened. So in July, so 2024, last year, Alpha Proof got silver medal standard outputs on the IMO. But what was important there was it required humans to first translate between natural language and formal language, which was lean in this case. And then it took 2-3 days to compute each problem. So that was last year. And this year, DeepThink takes inputs in natural language and produces proofs in natural language, and does so in about 4.5 hours, which is the time limit for IMO contestants. And it turns out, and this was a conversation we were having at lunch, is that Google, and I don't even know about OpenAI, but Google submitted their answers to the IMO committee, and the IMO committee went through that and verified the answers. But they do say in their press release that the committee did not verify the processes that were involved in generating the answers. So this is not a verification of whether everything was done as, per the rules of the IMO. I don't have an answer to that. But I just bring this up to point out that the experts were completely wrong 3 years ago. They were thinking that on that simple sort of math data set of high school problems, the best AI will be about 73% accurate. Now we are, if this is to be believed, we are at IMO gold medal standard already, right? So, and so this is the timeline. Basically, we've gone, in April 2022, most of you will remember DALL-E coming out and Stable Diffusion around this time. And then, ChatGPT comes out November 2022. And it just, this is a timeline. We are here now. So Google's Gemini DeepThink, there are a couple of Chinese open source models, Moonshot AI, DeepSeek, and this is the reasoning model phase. And to give you a context, all of that is these 3 years in the history of machine learning milestones, right? Which began sort of in 1958-59 with perceptron and Adeline, and all of the stuff that we are so excited about right now is just 3 years old, right? Right. I'll stop here. Thank you very much.
Yeah, we've had a lot of questions, but we'll take some quick questions, and afterwards I have a discussion.
Actually, it's a comment on this chain of thought thing, which I didn't want to make then. At least in some cases, there are provable results that next token prediction can't get some answers. For instance, with one layer transformer, you can't even get an induction head, can't even copy. So chain of thought effectively increases the depth of the transformer without actually having the depth of the transformer. So it's natural that, if you train the model to create a lot of intermediate tokens, it will generally get better at inference. You still want to align it, so you don't want all the intermediate tokens to be visible to the user. So it's not unnatural to assume that, the reward model will try to train the model to, do more chain of thought prompt, generate more intermediate tokens before generating the final answer.
So your point was it doesn't tell us why chain of thought in the original LLMs were working. I mean, I think the intuition is just still the same, that it's somehow allowing the model to put more and more information into the context and allowing it to backtrack if necessary.
I think you can do better. You can show in some cases that, if you have a sequence of tokens and you want to predict the right answer, and if the correct answer is of some form, like it involves some number of function compositions,
right.
And if you have only L layers in your transformer, you just cannot mathematically get the right answer in one token.
Right.
But if you do sequence of thoughts, you generate a lot of intermediate tokens. And so that basically increases the effective depth of the transformer by that amount. So it's just provably better.
Right.
Yeah, just a question about, verifying whether these artificial intelligence models are using reasoning. Reasoning, the stuff that we do, I mean, we are also a computer. We do, some processes go on. So what is reasoning even in the way we do it? How would you ever know that, their kind of reasoning is not our kind of reasoning, because we don't know what our kind of reasoning is?
I agree. We don't quite know how we can only, we tend to also kind of infer what we might be doing is if that we don't really know exactly what's going on. But we can behaviorally look at what is happening here and say, are these coming close to our reasoning capabilities? And we definitely do certain things that LLMs absolutely cannot. We can generalize really well. If we can learn abstractions about how to solve a certain problem and use those abstractions to solve problems in a completely different space. And LLMs are not there yet with those kinds of things. So there is some question about whether their reasoning ability, quote unquote, whatever that might be, is even generalizable the way ours is. We definitely are capable of abstracting things out and using those abstractions elsewhere. So just one example of what might be different. But you're right, we can only tell the differences by looking at the behavior, because internally we don't understand either LLMs or ourselves. Unless there's a computational neuroscientist who has a point of view.
There's the comparison with humans, and the theory you were saying you can do, right? Like in the chain of thought, you can just insert this thing or what about the giraffe?
Yeah.
So there actually is, in a sense, a way you can do something like that.
Yeah.
You can, like, how you do that. So you can do the very experiments that people do, like where for certain medical reasons, there are people whose corpus callosum has been cut off. So the two halves of the brain don't interact with each other. And then you can, typically, those people can do everyday life perfectly fine. But if I just put a partition in my visual space and I give one display to one side and one display to the other, I can kind of talk to the two different parts of my brain independently. So what you can do, something like you can show one half of your brain a task to say pick up a Rubik's Cube. So there's a table with like a bunch of different items. You give one half of the brain the task of pick up this object and you'll pick it up with that corresponding hand and pass it to your other hand. And then to the other half of the brain, you can ask, why did you pick up this object? It's almost like it's suddenly inserted this Rubik's Cube into it. And then the humans will come up with some sort of
rationale.
Oh, this seemed like the most interesting object on the day. So there really are ways where you can use cognitive science experiments to really put in these kinds of prompt injections into humans to then try to see what.
So I know about this work. I hadn't thought of it as prompt injection. That's exactly what it is. Actually, I'm going to use that from now on. This is Roger Sperry and Gazanika's work that you're talking, right? Yeah. Yeah, it is quite amazing. Thank you. I'm going to keep that in mind for the discussions. It's so cool.
The remark that you made about English and Chinese sometimes kind of reminded me of this thing that people say that bilingual people have, in some sense, much more flexibility in, or multilingual people have probably different representations, which then can sort of lead.
I mean, I think.
Is there some notion like that in these things, or it's still too early to even say?
So I can talk about one other interesting thing related to that. So one of the things we are doing with language models right now is we are going from an internal continuous embedding space. Every time you predict the next token, you enter a discrete token space, right? And people have been designing models where they're saying, why are we asking a language model to always come back into English, right? Or whatever language it might be? Why don't we let it churn internally in its high dimensional embedding space before it produces the next token? So it turns out that if you do that, if you let it do that, it can, in parallel, explore multiple chains of thought and then give you the final token before you loop back. So I think in cognitive neuroscience, I'm sure the bilingual stuff has been studied. I don't know the answer to that. I just remember an anecdote some IIT professor was telling me about how his professor used to talk when he was writing on the board, completely switch his monologue from English to Tamil and wouldn't even know he was doing it, but he would be talking to himself in English and Tamil, so yeah, something along those lines.
I mean, you train on two different sets of text data, presumably, these models, both Chinese texts and they probably are not overlapping in some.
They're all good at many languages. ChatGPT is pretty good at Hindi, for instance.
I mean, I have actually interacted. One of the things I did with the theory of mind was added one more level of indirection where I said, I'm going to ask the question in English, and you're going to answer me back in English. And then also translate it back to English for people who don't understand English, and it cracked it. Also, yeah.
So, but in those cases, are they trained on the Devanagari?
Yes.
They're not translating. There's no translation.
Whole internet, which has.
So it's, in some sense, you're saying language agnostic. It's just one more thing in the thing. Yeah. Anyway, thanks, Anil, for a very stimulating talk. I presume there are no other immediate questions, but let's thank him again.
Yeah, thank you very much. A pleasure.